Okay, good morning, everybody. I have just started the recording, so now we're being recorded. And today's topic is circuits. Let me share the screen here. Okay, do you see the PowerPoint?
Yep.
Okay, yeah. Thank you, Kelly. Once again, can you please read the chats for me?
Certainly.
They pop up. I feel free to ask questions as we go along. Okay, so I got an email asking me to go over Kirchhoff's rules, and I was planning to do that anyway. So I'll discuss a couple of things, talk about some circuits, and then introduce Kirchhoff's laws as we go along. But just out of curiosity, I was visiting another section where they did breakouts, and I noticed in going to the random breakout rooms that a lot of people don't know each other. Do you guys know each other? Let me exit from this for a second.
No. I've never met anyone in this class.
Yeah, is that typical? Is that?
Yeah, like Alex said, I recognize names. I have somebody who's in both of my classes or 3 of my classes this semester, but I've never met them before. I think if we were on campus, you would be able to recognize and get to know people you see all the time, but.
Yeah, exactly. All right, so maybe there's not time here, but what I was thinking of doing is just sort of doing a random breakout room, just so that you could meet a couple of people. Let me try to do that maybe at the end, because there's to go through. Anyway, that was a concern because with the Zoom format and everybody at home, it's easy to just not meet anybody. And physics is a collaborative activity. So, and if nothing else, you could meet other people in your major, in different classes and whatever, and have somebody to complain to, right? There's always something to complain about, right? Okay, that was one thing I wanted to mention. Give me some feedback on that at some point. Maybe email me or whatever, what your thoughts are. Other thing is that I have been posting, Collaborate will automatically record these sessions. And so those recordings are available to you, and I've been putting them into the content area along with the PowerPoints. And a couple of people have asked me to make them available outside of Blackboard, so I've been putting together a little YouTube channel. It's not quite open yet completely, so but I'll let you know as that develops. Okay, let me go back to this and begin the discussion of circuits. Okay. Here's the simplest DC circuit. So direct current. Pointer. We have a battery and a resistor, and when it's hooked up like this, you get a current I, and we know that these are related by Ohm's law. The voltage is the current times the resistance. So let's talk about each one of these components. Here's the idealized battery, and I'm emphasizing the idealized battery. It's just this part of that circuit. It provides a constant voltage across the terminals. That's the idealized of it, really, well, part of it. And then also provides whatever current the circuit requires. Those are 2 aspects of the idealization. No real battery is able to do this. And there's a way to model a real battery, which maybe we'll get to, where you just put a little tiny resistor in there. I think you talked about that briefly in class. Okay, so there's the symbol for the battery. Notice that one side of it kind of looks like a capacitor, except that one side is longer than the other. The longer one is at the higher voltage, so there's a plus sign. The shorter one's at the lower voltage. So if you go from A to B, there's a drop in the voltage. Similarly, if you go from B to A, there's an increase in the voltage. And it's not that bad to think about an analogy with just height. So if you go from A to B, it's kind of like going downstairs, right? Your altitude decreases. If you go from B to A, your altitude increases, like you're going upstairs. You can think of it as an escalator that the battery just takes you up. That's not a bad analogy. And now here is a resistor. And now we want to talk about the voltage change. If there is no current that flows through a resistor, then A and B will be at the same voltage. But that's not the interesting case. The interesting case is when there is a current. And of course, the current goes in a particular direction. So here I drew it going from A to B. So there's a voltage drop when traversing in the direction of the current, that is to say from A to B, given by Ohm's law, except that it's a decrease in the current. So that's why there's this little minus sign here. So VAB, that means going from A to B, there's a change in the voltage of negative I times R. So developing the analogy with altitude, and again, think about the current as flowing water. So A is at a higher altitude, B is a lower altitude, so the water flows downhill. And if you go from A to B, then you're going down in altitude. On the other hand, if you go in the opposite direction of the current flow, from B to A, you're kind of going up the waterfall, if you will. So your altitude goes from B, going from B to A goes up. So that increase in terms of electric potential from B to A is given by Ohm's law with a plus sign. Okay, so that's an important rule to know. If you go from A to B across a resistor in the direction of the current, you decrease in voltage. If you go from B to A, in this case, if you traverse a resistor in the direction opposite of the current, then you increase in voltage. Okay. Okay, so here is a more complicated circuit. It looks just like the circuit that I had before, except for this black box here. And this black box is a potentially complicated combination of circuit components. But the important part here to emphasize is that whatever it is, it may be something complicated, it has a net resistance, R net. And the battery basically can only sense that. If we anthropomorphize the battery can't see or hear the rest of the circuit at all. All it can do is feel this resistance. And as a result of what the resistance is, it puts out the current. And so Ohm's law applies in this way. The black box might be complicated, but its net resistance is R net, and the current that comes out of the battery is given by this formula here. So the task is then, how do you look at complicated circuits and make them more make them a little easier to understand and reduce it to figure out what the net resistance of a complicated system is. So there are a bunch of rules. Let's talk about resistors. Here are two resistors in series, and that just means one right after the other along wire. So this combination is equivalent to this one, where R series is the net resistance of this combination. And resistors in series just add together the resistances. So R1 plus R2 is equal to this R series, the effective resistance of the combination of two resistors in series. So that's easy. Again, you can think of sort of water flow, and the resistors are kind of like pipes. And the bigger the resistance is, the narrower the pipe is, perhaps. Okay. But if you think about it, if you've got some pipes with water flow, and you've got a certain amount of water flow going through R1, the same amount of water has to go through R2. So you have the same currents. In terms, back to talk about the actual circuit, the current that goes through one resistor has to also go through the other resistor, because there's nowhere else for it to go. It's not going to bunch up anywhere. We don't have a capacitor here. So that's important to realize. In this situation, the current through each resistor is the same, because it has to be. Where else is it going to go? Because no current is lost or created. It doesn't build up unless we have a charge doesn't build up anywhere without capacitors. Okay, so therefore, if these resistances are different, the current is the same and the resistances are the same, or different, excuse me. The currents are the same. If the resistances are different, then the voltages across each resistor will be different. You could just apply Ohm's law to this resistor by itself. V1 equals IR1, and then apply Ohm's law to this one by itself. 2 equals IR2. And so if R1 is different from R2, the voltages across each one will be different. And again, feel free to interrupt me if you have questions. The other kind of combination is, of course, in parallel, like this. We have a wire that breaks into two, and there's a resistor up here, and then a resistor down there, and then the wires merge again. So in this case, this net resistance from this part of the circuit all the way to the other one is this net resistance called R parallel, because these are parallel for obvious reasons. And the thing is that these resistors add in this sort of reciprocal fashion. So 1 over the net resistance is equal to 1 over R1 plus 1 over R2. Or you could write it this way. R parallel is 1 over, and then 1 over R1 plus 1 over R2, like this. So just a little bit trickier. Make sure that you add fractions correctly. You have to put things under with common denominators, and then before adding and such. I know you all know how to do that, but do it carefully. In the years I've been teaching this, careless errors tend to show up when you're handling fractions. Mainly because sometimes people don't write it in a way that makes it obvious to themselves as they continue. It's not that they don't know how to do it, it's just that they get confused by their own writing. So when you do these fractions, make sure you write them very clearly so that you don't make inadvertent mistakes. Okay, so in this situation, the voltage across each resistor, assuming there's some current going through, is the same. And that's basically because if you start up here, let's say this is a higher voltage and there's a lower voltage, you could go from here to there, either going through the top resistor or going through the lower resistor, right? If you are on the first floor and you want to go down to the ground floor, you could go through this escalator, or you could go through that escalator. And even if these resistances are different, your change in altitude will be the same. It has to be, right? So similarly, the voltage across R1 and the voltage across R2 are the same. Therefore, if these resistances are different, then the currents through the resistors are different. And so V is the same for each one. Apply Ohm's law to the top one. So V equals R1I1. Apply Ohm's law to the bottom. V equals R2I2. So if the R's are different, then the I's are different, because we know that the V's are the same. And again, if you think about water flow, let's say that you're up here at the higher place and you're looking at water flowing down to a lower place, and you have a thin pipe, let's say it's the higher resistance one, there'll be some water that goes through it, but not as much as one that goes through a much wider cross-section pipe, a thicker pipe. Right? Okay, so let's put these ideas into practice. Here is a sample circuit. Just a bunch of resistors, as you can see. And the approach now is to figure out what the currents are. See, it says I1 here. Excuse me. Some current comes out of the battery from the positive side, right? Conventional current comes out. That's the current I. Here at this junction, it splits into I2 and I1. And they come together again, and then we have current I going back to the battery. So let's figure out what these currents are. And like I had on the first slide, this upper part, this combination of these three resistors is sort of the black box that I had on the previous slide. There's some net resistance that the battery feels, and in response to that net resistance, puts out the current I. So to figure out what that current I is, we have to figure out what that net resistance is. And so we apply the rule that we just had. We look at the various ways these resistors are arranged and replace them with their equivalent resistors until we have just one resistor left. All right, so let's look at this parallel construction here where we've got the 500 ohm and 700 ohm resistor between B and C in parallel. The net resistance of that parallel construction, RP, is given here. So you add these things reciprocally. Right, so the net resistance 1 over, and then in the denominator we have the sum of 1 over 500 and 1 over 700 ohms. Put that in a calculator and I got this, 292 ohms. Now ordinarily I would keep the 292 ohms, but since I'm drawing this picture from this example, they did an approximation here. So they rounded this to 290 ohms. So see, they had this typed in here. So this parallel construction has been replaced by this net resistance of 290 ohms, which really should be 292. We'll go with that rounding for now. Okay, so now we just have these two resistors in series, and the net resistance of that is easy. We just add the 400 and the 290 for a net resistance of 690 ohms. So this more complicated circuit reduces to this one, at least from the point of view of the battery. The battery just feels a resistance of 690 ohms, the net resistance of that whole construction. Again, interrupt me if you have any questions. So the current that comes out of the battery just comes from Ohm's law now. Right, so if the current plug in 12 volts, which is what the battery is, and the net resistance 690 ohms, gives us this much current, 0.0174 amps. A little bit of current that comes out of the battery. There's been some rounding that's been going on here. Okay, so now let me go back to our thing. So we know how much current comes out. Now we can examine this reduction of the current of the circuit and then go back to the original one step by step. So in this intermediate reduction of the circuit, we see that there's only one way for the current to flow. So in this version of it, all the currents are the same, given by the number we just found. In particular, we know the current from A to B is that, and it goes through that single resistor. So we can figure out the voltage change from A to B using Ohm's law. Notice that if we go from A to B, we traverse the resistor in the direction of the current. So the change in voltage is a drop in voltage equal to I times R. So plug in the value of I, plug in the value of R, and we find out that the voltage change from A to B is this. So it's a drop of 6.96 volts. Again, there's been a little bit of rounding.
Dr. Barreto, so
Yes, go ahead.
it's negative because the current's going in that direction and we're jumping down the stairs from A to B. That's why you have
Exactly.
Okay, thank you.
Yeah. It's important to have in mind which way the current is going. And remember that we had, the long part of the battery is the plus side, so that the current comes out of there and then goes around the circuit and comes into the shorter side. So the current's going that way. From A to B, we go in the same direction of the current, so it's like going down the waterfall. There's a drop in voltage. Okay, thank you for the question. And similarly, the drop in voltage from B to C is given by, once again, Ohm's law. The same current that we figured out going through this net resistance of 290 ohms. So from B to C, there's a drop of 5.04 volts. Again, with a little bit going on. All right, so 2 drops in voltage. Here we go. Now we know the current is I that comes out of the battery. We know the voltage drops from A to B and from B to C. And now notice that if you do a counterclockwise round trip, starting from, say, point A, you will encounter the following changes in voltage. First, there's a drop, as we just figured out, of 0.696 volts going from A to B. And then there's another drop of 5.04 volts going from B to C. And now, as we go around the circuit again, we now come across the battery. And we go across the battery from the short to the long side, which means we're going up in voltage. We're going back up the escalator. So there's a plus 12. And we return back to A. Now, if you add all these up, you get 0.
You need to say clockwise, right? Not counterclockwise?
You are correct.
Okay.
Let me change this now. Yeah, certainly, this is clockwise. Thank you for pointing that out. Something in the chat?
Julie and I had the same question at the same time. So.
Oh, okay, good. Thank you for keeping me honest here. But what I wanted to emphasize is that as you do this, the change in your voltage, the net change in your voltage as you go around the circuit and end up in the same place you started is 0. And it better be 0. Just like if you start on the, say, 3rd floor and you go down a couple floors and then go back up a couple floors and you end up in the exact same part when you started, your altitude better be the same. Otherwise, it would be really strange. Right? It would be very surprising if you did a round trip and your altitude had a net change. Okay, so that is Kirchhoff's loop rule. It is just that simple idea. If you start somewhere and go around, your net voltage change has to be 0. And it's not any more mysterious than if I stand somewhere and I go around the building and return back to where I was, my altitude better not change. Was there something in chat?
Julia said she loves that analogy.
I didn't hear that. I'm sorry.
She loves that analogy.
Oh, okay, good. Yeah, cool. Now, I'm not entirely sure how to pronounce this guy's name. I've always said Kirchhoff, but of course it's it's a German name, I think. So it would be Kirchhoff, but I've also heard Kirchhoff. Not sure exactly what to tell you. In fact, I even looked online for that you can find these recordings of how names are pronounced, and I found 2 different pronunciations for the same guy's name. So I still don't know how it's pronounced. Anyway, now that we know the voltage changes from B to C, we can go back and plug back in the actual circuit, which has these 2 other resistors, right? This is the actual circuit now. And we realize that the current splits when it goes from B to C. Some of it goes through the 500 ohm resistor, call that I1. Some of it goes to the 700 ohm resistor, we'll call that I2. And then those 2 currents recombine, and then we have the current I once again. Again, you can't lose any current, you can't create any current. So when they combine, it's the same amount of current as went in. So I equals I1 plus I2. And that is Kirchhoff's junction rule. Again, it's just the simple statement that you don't create or lose any current. When it splits, everything is accounted for. You can imagine water flowing through a pipe. This has to also be true. The flow of water has to split evenly, and you don't lose any unless there's a leak. We don't have any leaks, or there's an accumulation, in which case the pipes would burst eventually. So that doesn't happen, and so we have Kirchhoff's junction rule. So it's a very intuitive idea. All right, so now we can find the current through the top resistor. So we know everything so far, right? We know the current through 400, the 400 ohm resistor, that's this. We know the voltage from A to B. We know the voltage from B to C. What we're missing is the currents through the top and bottom resistors I1 and I2. So let's find I1, the current through the top resistor. Just apply Ohm's law to the top one. We know the resistance. We know the voltage change. That's this. So just plug it in. Right, so the current is 0.0101 amps. Okay, and you notice that I forgot about the minus sign. I didn't forget. I left out the minus sign in doing this. Because when I write down the current, I'm writing down the magnitude of the current, and the direction of the current is given by the arrow. It makes sense that if you go from B to C and it's a decrease in voltage, that the current would go from B to C. And similarly, the current through that's supposed to say 700. I have 600. Current through the bottom resistor is just the same Ohm's law applied to just that resistor. Same thing, except the denominator is different, and we get 0.0072 amps. And we can go ahead and check the junction rule, take I1 and I2 and add them together, and we get the same as the current I. And you're going to say, well, what about the 4 and the 3? Well, there was some rounding along the way. So if you do everything, and I have done this, you do everything with more precision, you see that these are the same numbers. Okay, any questions at this point?
No.
Okay. All right, a brief review of Kirchhoff's rules. A junction rule is simply that no current is created or destroyed. Here's a junction. Let's say current I1 goes in and currents I2 and I3 go out through the two branches. I1 equals I2 plus I3. Just the statement that no current is created or destroyed. You have to account for everything. And the loop rule, as I said, is just this. If you traverse a closed loop within a circuit, the net change in voltage is 0. And that applies to any loop that you choose. So I could traverse this circuit starting from A, say, go through this resistor, and then say I want to go through the 500 ohm resistor, and then go through the battery, return back to A. Net voltage change has to be 0. Or I could go from A to B through the lower resistor, continue, and go back to A. Once again, the net voltage has to be 0, just intuitively. So if you write that down, you can get two equations because there are two loops. And there's even a third loop. If I start at B, I could traverse this resistor, come back, and then traverse 500 ohm resistor in the other direction, return to B. My net change in voltage has to be 0. So wherever you start, as long as you go back and return to that, net change in voltage is 0. And then here's a summary slide for the combination of rules. Excuse me, the rules for the combinations of resistors. So I'll skip over that and jump now to the capacitors. I think that you already discussed capacitors in an earlier chapter. Capacitor is just basically two plates that are near each other that introduce a break, a physical break in the current, in the circuit. And so there's an accumulation of charge there. As current flows, charge accumulates there. It builds up to a certain point. The capacitor can hold a certain amount of charge given by this. So the amount of charge is the capacitance times the voltage difference from one plate to another. And the meaning of this Q is that I have a certain amount of charge Q built up on one side, and then the opposite sign of a charge on the other plate in the same amount in magnitude, right? So I could have plus Q on one side and then minus Q on the other. And I would say that the capacitor is holding charge Q. The units are farads. 1 farad is a coulomb of charge stored per volt across the capacitor. Farads are gigantic units, so you often hear, you talk about microfarads or millifarads or small amounts of farads. All right, so now we have these rules for combining the capacitors. Here are two capacitors in series, and it turns out that capacitors in series add reciprocally, just like the resistors in parallel did. Except that capacitors, if they're in series, then this math applies. And the thing to know about capacitors in series is that in this situation, where I have two capacitors in series hooked up to a battery, the capacitors will hold the same amount of charge. For example, if I hook this up, as soon as I hook it up, current comes out of the positive side of the battery, builds up on this side of the capacitor, and so that'll be positively charged. That'll push away positive charges from the other side of the capacitor, and those charges will migrate over this side and build up on this side. This will be negatively charged. Excuse me, that'll be positively charged. Right, so current comes out, this left side is positively charged, the right side is negatively charged, and then this side ends up being positively charged. The left side of C2 is positively charged, the right side is then negatively charged, and the current continues. But they both have the same amount of charge. And that maybe is clear because you see this H-shaped, long H-shaped wire in the middle here. Notice that it is not connected to anything. So it's neutral. Right? If there's a charge buildup on this side, then there's the opposite charge buildup on the other side. And so then you can conclude that the charge held by these capacitors is the same. And remember that when I say capacitor C1 has charge Q, it means that there's plus Q on one side and minus Q on the other. Okay, so again, if you apply now the Q equals CV rule to that situation with the same amount of charges on each one, if the capacitors are different, then the voltages across these capacitors are different. I should have written out the Q equals CV here. The Q's are the same. If these are different, the V's are different for each capacitor. Well, there it is. Yeah. Okay, if you have capacitors in parallel, then these just add together. So it's capacitors and resistors have just the opposite math applied to them. In fact, you can sort of imagine that this plate, since it's physically connected to the other plate, you could imagine just merging the plates, and you just have a single capacitor with a larger area. Right, so in this situation, once again, in a parallel construction, the voltage across each capacitor is the same. As a result, if the capacitors are different, then each one will hold a different amount of charge. And so Q equals CV with the same V for each capacitor. If the C's are different, then the Q's are different. Okay. The voltage, again, has to be the same because I could start at this end of the voltage, excuse me, of the battery, and take this either path, either the lower path or the higher path, and it has to be the same change in voltage.
Can I ask a weird question or a random question?
Go ahead.
How would a capacitor be different?
You mean the capacitance?
No, you're saying like the capacitors, if they were different, then the charge in them would be different. But how would they be different? Like, is it literally size?
Their capacitances would be different. So physically, if these are parallel plate capacitors, they would have, say, a different area, of the plates.
Okay.
Or they could have a different dielectric in between them, for example.
Okay.
Or a combination of both of those. Right? So you can imagine if the plates are bigger, then it's able to hold more charge.
Yeah, I think I completely forgot that when we were talking about capacitors a couple chapters ago, that it was like over the area, whatever. So thank you.
For parallel plate capacitors, there are different kinds of capacitors, but whatever their geometry is, their capacitance is this number C, measured in farads. All right, let's work out an example. And once again, it's just this circuit, and we follow along and break each part up and reduce it to a simple circuit. So let's find the charge on each capacitor and the voltage across each capacitor. Well, we have here a parallel construction, and capacitors in parallel add. 3 plus 2 is 5, as I put it down here. So we can replace this parallel construction with a single capacitor of capacitance 5 microfarads. And then we've got two capacitors in series. Remember that the net capacitance then is sort of reciprocal sum, like this. 1 over 1/5 plus a third. A fifth and a third is all in the denominator. That works out to be this number, so I could replace that whole construction with a single capacitor of 1.875 microfarads. And the battery, again, if we anthropomorphize it, can't see or hear the whole circuit. All it does is it feels a certain capacitance and puts out a certain current according to the rules. Or in this case, the thing to say is that it puts out a certain amount of charge, which accumulates over there. So we apply Q equals CV to this effective capacitor. Excuse me. The total charge held by that net capacitor is 7.5 microcoulombs. Please don't confuse this C, which means coulomb, with this C, which means capacitance. So that's the amount of charge that has left the battery. So now we go back to the actual circuit. We know that 7.5 microcoulombs left the battery. So where did it go? Well, the first thing, if I can look at this one, that charge has to be accumulated here, because where else is it going to go? So I know that the charge held by this capacitor is 7.5 microcoulombs. Now I can apply that Q equals CV rule to this capacitor to get the voltage across it. So it's Q over C, the charge that we know, the capacitance that's given, and so it's 2.5 volts. All right, so there's a difference of 2.5 volts across this capacitor. And now remember that this, because we have a parallel construction here, the voltage across each one of these would be the same. So let's do a loop. Let's say we start at the lower left-hand corner. Or no, let's say we, let me do this. Well, if we start here, I guess these are kind of out of order. So let me go ahead and fix that so I don't confuse people. There. Okay, so if I start in this lower left-hand corner and I go around, I have an increase of 4 volts. That's this 4 volts. And then a drop, regardless of which one I go through, there's going to be a drop of X volts. X is unknown. And then a drop of 2.5 volts here. How do I know it's equal? Because I know that this negative sign is connected to this one. So that's the negatively charged side of the capacitor. This one's positive. So I go from the positive to the negative side of the capacitor, I get a drop of voltage. Then I end up at the same place I started, so the change in voltage has to be 0. Solve that for X, and I have 1.5 volts. So I know that the voltage across each one of these capacitors, the 3 and the 2 microfarad capacitors, is 1.5 volts. Then I can apply Q equals CV to each one of these capacitors to get the charge on each one of them. Right? I know the capacitance, I know the voltage drop across each one of them, so I get the charge on the upper one is 4.5 microcoulombs, and the lower one, same formula, is 3 microcoulombs. And notice that, as expected, 3 plus 4.5 is 7.5 microcoulombs. So this accumulates 7.5 microcoulombs. And since this chunk of wire here is neutral, then the combination of the charge on this one and this one has to be 7.5. Okay. So here's my summary of the rules for series and parallel capacitors, just like resistors, except that it's the other way around. All right, so I'm going to do another example here, but before doing that, I'm going to take a quick screenshot of attendance. So give me a second while I do that. Feel free to ask a question if you have one right now.
I do have a question for the place where not the parallel capacitors, but the one that was in the top right. Would the right-hand side be positive in that capacitor and the left would be negative?
Okay, unfortunately, I did not know what you said because
That's
my computer is popping up all these windows, which is screwing up what I'm trying to do here. Okay, but now I have succeeded. Can you repeat your question, please?
Can you go back 2 slides? So where the arrow says V equals 2.5 in the top right corner of this,
Yep.
that right side of that capacitor would be positive, correct?
No, the right side is negative. See this negative side of the battery?
Yes.
So that is negative, and so that comes over here, and okay, that would be positive.
Okay, all right.
Sorry.
I just want to be sure, 'cause I'm like, the way that I'm looking at it is I feel that it should be positive, but that doesn't change how the math is done. Because you're minusing 2.5 because it would be on the left side. Wait.
No, let me. Yeah, you can imagine the current comes out of the positive side. So this turns out to be positive side. This is the negative side. So if this is the negative side
Wouldn't
of,
it be
of this one,
opposite?
then this would be the positive side. This would be negative, and that's connected to the negative. So yeah, that's right, isn't it?
I
If I
thought
start here, I go up 4 volts, and then down and down. So that's,
Read out.
what did I
I
just say? Hold on a second. So this is the positive side. So this has to be the positive side. And then you go down, this is negative, and this is positive, and that's negative. That's what I said, isn't it? I'm confused.
I know I'm confused too. I think I'd have to draw them because I feel like if the 4-volt one on the battery part of it is positive, then where you have the parallel capacitors on the top left, the far left of the capacitor should be negative, and then the right should be positive because it's opposite.
This is positive.
But
This is
wouldn't
positive.
those two
And negative and negative. And positive and negative.
so the negatives are on the same side, and the wire that
Yeah.
would be net though? Where would
So
the
let's start at the lower left-hand corner. I go up in voltage, down in voltage, down in voltage. So yeah, it's got to be like this. Yeah, the battery, right? The positive side of the battery is where the current comes out. So there's a net, there's a conventional current that comes out and it builds up on this side. So those are net positive charges, causing the other side to be negative, which means that, the positive charges that were there, if you can imagine that, get pushed to this side. Remember that it's a metal, and so it's actually the electrons, but let's think about it as positive charges.
Okay.
Get pushed over here, so that's the positive side. Therefore, this is the negative side, and that's connected to the negative side of this one.
So really it's not really related to, I think I was relating it directly to the battery and that it would have to be the opposite, but it just has to do with the capacitors pushing them on each side.
Yeah, and remember that there's no current flowing once this is set up, because there are physical breaks in the current, in the circuit, right?
Okay.
So whatever voltage this lower side is
It should be the other side. Okay.
is the same as this side, because it's physically connected.
That makes sense.
Good, thank you for that. All right, so let's quickly do this last question problem here. I've got a couple minutes. I've got 6 minutes. Okay, here's this arrangement with 2 batteries in it. And I wanted to do this example because in order to figure out what the magnitudes and directions of the currents are through each resistor, I don't know what it is at first because I've got these 2 batteries. And you see they kind of compete against each other. The top one has current that goes out the top. This one has current that comes out of the bottom. And then what happens? I'm not sure what happens. So the way to approach this problem is first begin by guessing. Label the currents through each label the current through each resistor and guess their directions. I'm not confident that I know the direction of, say, this current here or this current. So I'm just going to guess. I'm going to guess that, current I1 is this way, current I2 is that way, current I3 is that way. And then I just proceed, try to solve the problem. We apply Kirchhoff's laws to get the 3 equations, There's 3 currents, so I need 3 equations. We'll then solve those 3 equations for the unknown 3 currents. All right, so let's set that up. Apply Kirchhoff's laws to get these 3 equations. First of all, let's apply the junction rule to A. We have I1 flowing in, and I2 flowing out, and I3 flowing out of that junction. So I1 equals I2 plus I3. No current is created or destroyed. So draw a box around that, and we'll keep that equation. Then let's do the the loop rule. And I'm going to begin by doing a loop starting at B. I could start anywhere, but I'm going to pick this point B and go through the upper part of this circuit. See, I sort of grayed out the bottom one. I'm going to do a clockwise loop around the upper part of the circuit. So first of all, I go up because I'm crossing the battery in the direction from negative to positive, up 9 volts. I drop a certain amount of voltage across this resistor because I'm crossing it in the same direction of the current. So minus 24 ohms times I1. Make it to A, and then I could traverse that resistor again in the same direction of the current. So minus 11 ohms times I2. Then I'm back at B, so that all adds up to 0. There's an equation, which I'll keep. Now I do the loop rule for the lower loop. So you have grayed out the upper. And again, I'm going to start at B, and I'm going to go counterclockwise this time. Then I could start anywhere. I could go in any direction as long as it's a loop. So if I start at B and go counterclockwise, I cross the battery and go up 12 volts. And then I cross this 40 ohm resistor in the direction opposite of what the current is as labeled. So that means I go up 40 times I3, plus sign here. And then I traverse this one in the same direction of the current, so there's a minus sign. I end up back at B, so that has to all add up to 0. All right, so these are the three equations that we got: junction rule, loop rule, upper loop, loop rule, lower loop. That's the setup. That's what you really need to understand here. Solve these three equations with three unknowns. I'm going to skip the algebra, but I do have the slides. So when I post them, you'll be able to see them if you wish. Here's the result. I figured out that I1 is this many amps, and I2 is this many amps, and I3 has a negative number of amps. So what the heck happened here? Why do I have a negative sign? That means that my initial guess for I3 was in the wrong direction. So that negative sign means that I had guessed that I3 goes, down here and to the left over here. That's wrong because I have that negative sign. It actually goes to the right through that resistor and up over here. So if I reverse the direction of those arrows, I can replace that with a plus sign now. And then I have this solution of the problem with these directions and these numbers of amps through each ohm. Excuse me, through each resistor. Okay, so remember that. That's kind of key. At first, I didn't know the direction, so I guessed, solved the problem, and wherever I had a negative direction of, a negative value of the current, it just meant that I had guessed the direction wrong, and I can go back and flip it.
Dr. Barreto?
Go ahead.
Could you go over the junction rule equation you got for the top one?
There it is. Junction A, we have I1 flowing in. That's the left side of the equation. And flowing out of it is I2 and also I3. So the amount of current that comes in gets split into these two pieces, but the sum of the two pieces is the same as what came in.
Thank you.
It's literally what goes in equals what comes out. Okay.
Yes, that's helpful. Thank you.
Okay, I see that I'm out of time now. So I will post these slides, and I do have the algebra that I showed you. Again, I have some additional problems with solutions written out, which I'll also post to make that available to you. I can stick around for maybe 5 or so minutes if anybody has additional questions. Other than that, I hope this was helpful, and please have a good weekend. Oh, I'm going to have an office hour tomorrow. I'm not sure the time yet. I'll post it and let everybody know.
Excellent. Thank you.
Okay, good. Hope I was useful. Everybody have a good weekend.
Mm-hmm. I have to get to class in 3rd.
See ya.
Have a good day.
You too. Bye, everybody. I'm going to stop the recording now.